Hello everyone. Here's a quick thought. Have you ever wondered how waves travel so smoothly, almost like they have their own little guides? Well, Huygens had an idea that every point on a wavefront is like a tiny wave factory, producing its own mini waves. It's like a stadium wave where every fan rises just after the one next to them, creating a ripple around the crowd. Huygens' principle says that every point on a wavefront acts as a source of secondary wavelets, and these wavelets spread out only in the forward direction with the same speed as the original wave. Imagine throwing many tiny stones into a pond from a line, each making ripples that grow and overlap. The new wavefront is the outer edge of all these tiny ripples, forming an envelope tangent to spheres centered at each point source. This neat idea explains why waves travel straight in uniform media, known as rectilinear propagation, and it also reveals where simple ray optics fall short, especially in understanding diffraction, which is the bending of waves. Mathematically, the wavefront position at some future time equals the envelope formed by spheres of radius r, which is the wave velocity multiplied by the time interval. So if v is the wave velocity and delta t is a small time step, the new wavefront is at radius r equals v times delta t. Pretty elegant, right? This principle forms the backbone of understanding not only classical waves but also light as a wave. Now, let's picture the different shapes of wavefronts and how they relate to their sources. Imagine a pebble dropped into a still pond. It creates circular ripples, but in 3 dimensions for light or sound. These are spherical wavefronts, expanding uniformly in all directions from a point source in a medium that's the same in every direction, which we call homogeneous and isotropic. If you step far enough away from such a source, the curved surface of these spheres looks practically flat, forming what we call plane wavefronts. Think of standing very far from a fireworks explosion. The light rays entering your eyes appear nearly parallel like flat waves, even though they actually came from a point. Then, there are cylindrical wavefronts, which emerge from sources that are more like lines than points. Picture a stretched out sparkler. Wavefronts here are circles in cross-section, like ripples spreading out into dimensions. To tie it all together for a point source, the radius of the wavefront increases evenly over time according to the equation r equals v times t, where r is the radius, v is the constant wave speed, and t is the time elapsed. This geometric view helps us visualize and predict how waves propagate in different situations. Here's where things get interesting. Huygens' original idea ran into a bit of a puzzle. It predicted that these secondary wavelets should spread out in all directions, including backward, but in reality, waves usually move forward. So why don't we see waves traveling backwards? To fix this, scientists like Fresnel stepped in with the Huygens-Fresnel principle, which cleverly restricts those secondary wavelets to just the forward hemisphere. They introduced something called the obliquity factor, which is basically a way to weight the wavelets so energy flows mostly forward. Think of it like a flashlight beam. It's brightest straight ahead and fades off toward the sides and behind. The energy distribution E of theta, where theta is the angle from the forward direction, follows E theta equals E naught times cosine theta. This means maximum energy or amplitude points straight ahead and decreases as the angle increases, zeroing out directly backward. Physically and geometrically, the new wavefront forms as the common tangent or envelope of these forward-focused wavelets. This tweak neatly solves the backward propagation mystery, keeping waves marching onward just as we observe. Let's see how Huygens' principle explains everyday phenomena like reflection and refraction, the bending of waves at boundaries. Imagine a wavefront approaching a wall. Each point on this incident wavefront becomes a source of new spherical wavelets after it hits the boundary. When these wavelets bounce back, the reflected wavefront emerges, and by symmetry of the wavelet's envelopes, the angle of incidence equals the angle of reflection, just like a ball bouncing off a wall at the same angle. Now, when the wavefront passes from one medium to another, things get even cooler. The wavelets in the second medium spread with a different speed. Using the wave velocity v1 in the first medium and v2 in the second, and angles of incidence I and refraction r, the wavefront geometry leads to the relation v1 over sin I equals v2 over sin r. Rearranged, it becomes sin I over sin r equals v1 over v2, which we call the refractive index nu. This formula is nothing but Snell's law expressed elegantly through wavefront construction. So, Huygens' principle doesn't just describe wave propagation, it geometrically derives the reflection and refraction laws fundamental to optics. Next up is diffraction, one of the coolest wave effects. Diffraction is when waves bend or spread out after passing through small openings or around obstacles, something ray optics can't explain. According to Huygens' principle, those secondary wavelets coming from every point on the wavefront interfere constructively and destructively, creating the characteristic diffraction patterns of bright and dark fringes. Imagine waves squeezing through a narrow slit. Their bending angle depends on the wavelength lambda and the slit width a. The central bright region's angular width theta is given as theta equals lambda divided by a. So, the smaller the slit or the longer the wavelength, the wider the diffraction pattern. This principle gives us a mental picture of waves bending by recombining those secondary spherical wavelets, showing that even light waves can spread and interfere, not just move in straight lines. To wrap it all up, let's revisit some key ideas from Huygens' principle. We started with R equals V times T, where R is the wavefront radius, V the wave speed, and T time, describing uniform wave expansion. Then came the famous Snell's law form, sin I over sin R equals V1 over V2 equals mu, relating angles and speeds during refraction. The obliquity factor, E theta equals E naught times cosine theta, ensures waves mainly push forward, fixing the backward propagation problem. And finally, diffraction's angular width theta equals lambda divided by a shows how waves spread after passing through apertures. The big takeaway is that every point on a wavefront acts like a mini source of secondary wavelets moving forward at the wave speed, building new wavefronts and explaining phenomena like reflection, refraction, and diffraction. This wavelet construction gives us a powerful geometric and physical understanding, going beyond simple ray optics. Remember, this is how light really behaves, not just straight lines but waves spreading, bending, and interfering. That is it for today's concept. Physics is fun when you can laugh and learn. See you in the next session.